Hello everyone and welcome to our first video of Module 5. Module 5 is going to talk about the field effect transistors or FETs. The first thing we'd like to start with is just to have some similarities or differences between the field effect transistors and the bipolar junction transistors that we covered in our previous module. So among the similarities, field effect transistors have the same function as bipolar junction transistors. That is, they can be used as amplifiers, they can be used as switching devices, and they can be used as impedance matching circuits, as we will be seeing later on. However, there are some differences between field effect transistor and bipolar junction transistors. For example, field effect transistors are voltage controlled devices. On the other hand, our bipolar junction transistors are current controlled devices. If you remember, we control the on-off based on the current that we are going to have. Here, the control device or the control factor of the operation of our field effect transistor will be the voltage itself. Field effect transistors, they have higher input impedance. On the other hand, the bipolar junction functions, they have higher gains. The field effect transistors are less sensitive to temperature variations and are more easily integrated on ICs, and this is one very important feature, that no matter how much the temperature is varied, the operation and the functionality of the field effect transistor will not be changed. And finally, field effect transistors are generally more static sensitive than the bipolar junction transistors. So as such, if we would like to talk about the types of field effect transistors, we will be seeing that we have something called junction field effect transistor, which is JFET, and there is something called MOSFET, and MOS goes for metal oxide semiconductor. So therefore we have metal oxide semiconductor field effect transistor, known as MOSFET. Now this MOSFET could be of what we call the D type or the E type. This has to do with the way, what we call it, the depletion of ions or electrons in the IC. So that will be fine. We just don't care very much about those ones for the time being, but we care about that. At least we know we have something called MOSFET, and we have the D type, and we have the E type MOSFET transistor. Now if you look okay, now we continue by saying that if we look at the construction of JFET, just to give an idea, it's nothing but an N channel or a B channel transistor. And usually, as an example, this is here, it's called the N channel. You can see how it's done, but that's fine. You don't have to go into these details. All I want you to know is that we do have something called the drain and source, and you can see that the N channel is connected to both the drain and the source. We have a gate which is connected to the B channel. So the N channel is connected to the drain and source, and the P channel is connected to the gate. And we will concentrate on, in most of the applications, they do have N channel JFET. The symbol for the N channel JFET, definitely we're not gonna draw it always like this. Instead, we will be going and seeing the symbol, and this is the symbol for the JFET transistor. If you recall, our JFET is this one. However, our P bipolar junction transistor, we used to have it something like this. If you remember, that was the one. So this is a little bit different. Here you have it just a straight line, and you have an arrow for the gate, and here you have the drain, and here you have the source. So there will be a voltage called VGS between the gate and the source, and there will be a voltage between the drain and the source. It's called VDS, and depending on the voltage here, we will be seeing later on with the characteristics how we can control the current ID, and of course that is based on the voltage that we have as VDS. So GFET operating characteristics mentioned that you have three basic operating conditions. The first one is if you have VGS here less equal to 0 exactly, this means that I'm gonna have a short circuit between this point and this point. If VGS is 0, this means that they are the same potential, so it looks like a short circuit. Okay, and as such VDS will be increasing to a certain value. The other case will be if you have VGS less than 0, again VDS will be some positive values, and finally the voltage controlled resistor, as we will see. So if I just look at the characteristics, and I will start by the case where VGS is equal to 0, as I just said. VGS is equal to 0, this means that here I have the voltage. Okay, let me just draw it again here. I will just say that this is what I have. This is VGS, this is S, and this is my drain, and this is my gate. So if this is equal to 0, this means, as I said, I will have simply the gate and the source are as if they are grounded. So if you start for this VGS increasing the VDS, which is here, VDS, then you will see that you will have an increase in the current ID. Actually, this is ID here. So what I will have, as I said, as I increase for a certain value equal to 0 for VGS, I increase the VDS, and I will be seeing this kind of characteristics. As you can see, it's more or less a straight line, and then there will be some kind of a knee point, and then after some voltage VP, you will see no matter how much you increase VDS, you will have no increase in the current ID. At this point where I have no more increase in the current ID, for any further increase of VDS is known to be the pinch off point. So this is the pinch off point. The corresponding voltage, we will call it VP. It's not anymore VDS, it's called VP, and the corresponding current will be IDSS instead of saying ID. So they say that ID is at saturation or maximum. It is referred to as IDSS, and the ohmic value of the channel in that case will be the maximum value of the ohmic resistance. We will be seeing in a minute that what if I change VGS, and VGS now here we'll start saying that we'll take it more and more negative. So again, this is our transistor, and we have here, if you remember, this is how you connect it, and here you have your G, here you have your G, here you have your S, and here you have your D. So this is my ID, and this is my VDS. Now VGS is here, and I can start by changing it. This is the case we just discussed for 0 value of a voltage VGS. Now if I start decreasing this voltage, let's say to a -1, then the characteristics is similar in shape. However, the line here becomes having more slope, less slope. so the slope is less, and as you can see, the pinch of point is now moved a little bit lower. So for the case, as an example, for our case here, pinch of voltage was equal to 5, let's say, volt, for VGS equal to 0. The value for VGS equal to -1 could be somewhere here. It could be like 4.5 or something. If you go to for VGS equal to -2, you can get it here. It could be only 3 volts and so on. Now, eventually, and you can see for each case, you will have the current decreasing. As you can see, if I have this current equal to 8 milliamperes here as an example, for VGS -1, it's gonna be like, let's say 4.5. For -2 volts, it becomes equal to 2 milliamperes. If you have -3 volts, it could be like 0.5 milliamperes. And for VGS equal to -4, and this is something interesting, we find out that for this transistor, the ID current is equal to 0. So you can see here that we mentioned eventually IDE reaches 0 when VGS at this point is called the VP, or what we call the VGS off. That would make it not operating properly. So again, this is what we just mentioned, and if you wish, you will be able to see that if the transistor is operating in this region here, then it's gonna be in what we call it the ohmic region. And if it's operating in the upper region, which is the right region, in that case we call this region the current source region. So if you wish, we call this one is the current source region, which is of course the saturation region. And we can calculate what we call it the resistance of this in this region here, as which we call the drain region resistance, as RD is equal to R0 over 1 minus VGS over VP. And we will be seeing in our next, of course we will be seeing in the next slides how we can calculate the current ID with a certain formula, which is in here. So the JFET transfer characteristics, we will just mention that the transfer characteristics of input to output is not as straightforward as in the case of the JFET, as in the case of the BJTs. In JFET transistor, it's a little bit more. If you remember, in the BJT, the relationship between the current I base, and which is the input, and the output current IC, it was so simple. If you remember, we just say it's nothing that an alpha. So alpha IC, if you remember, it was alpha times IB. So very straightforward, where alpha is a constant. Here in JFETs, the relationship of VGS, which is the input, and the drain current ID, which is our output, is something like this. Of course, we were able to get for a certain value of VGS, we got what is the value of IDSS, and we know what is our value of VP, and we have the value that we are just pitch off value, and here this is the value of our voltage that we are interested in. And as I just said, the symbol looks like this one. As I said before, it's so simple. As you can see, we have the here you have the gate, here you have the source, and here you have the drain, and we said this is our voltage. Controlling this voltage will control this current depending on the value of the VDS that we have. So we have what we call it the JFET transfer curve, which means that if I have these characteristics for my JFET, can you draw for me the relationship between ID and VGS? Of course we can do that. It's so simple. All what you need to do is just to draw another axis that is parallel to this ID axis here and has the same numbers. And all what we need to say is that, okay, we will look for this value of VGS, which is minus 4, as an example, for 0 here, I know that for VGS equal to minus 4, the value of ID equal to 0. So I will go here and say, okay, ID, this is ID equal to 0 for the value of minus 4 VGS. Then I will increase. I say, okay, this is minus 3, so this is minus 3 here. What will be the value? It's exactly the value we have at the saturation here. So I will just move it as if it looks here, and then at minus 2, this is minus 2, but I will just go here and see what is the intersection between minus 2 and this one. So this is the point. What is the minus? And with minus 1, I have it. Sorry, with minus 1, I have this is minus 1, and this is the one, and this is the point. And with 0 value, I have this 8, and therefore I have 8. So that will be the graph or the characteristics. So if I would like then to plot the J-fit transfer curve using my IDSS and VB, which is VGS of values found in a specification sheet usually given, the transfer curve can be plotted as follows. First thing, we start by saying, okay, we have VGS equal to 0. That's number 1. I will go and calculate what is ID from my equation here, from this equation. I know what is our VB, I know what is IDSS, therefore I will just substitute by saying for VGS equal to 0, it's clear for this is 0, this is only 1, so ID is equal to IDDS. And then if I have any other value, more, or of course it will be in the negative, VGS minus 1, minus 2, minus 3, I will just substitute and see what will be the value that ID corresponding to my VGS. So here, this is step number 1. Step number 2, we said that we will solve for this case, which means that I will go and substitute for VGS what VP, which is the maximum value we have, which is, the value of VP, it will be equal in the equation, VP, VGS over VP, and 1 minus here multiplies by IDSS. So if VGS is equal to VB, then this will be 1, and therefore 1 minus 1 is equal to 0, and therefore I have ID equal to 0. Then we will start by solving for VGS equal to 0 to VP. So we start increasing VGS from the 0 that we had at the beginning to 1 to minus 1 to minus 2 to minus 3, and we will see how the values will be. And we can do that here in this example. As an example, I have this transistor, and you can see in this specific transistor, which is this example, at least I know that IDSS is equal to 8 milliamperes, and I know that VGS here, okay, which is VB or VP is equal to the one corresponding to minus 4 volts. So if I have those two, I can go to these equations and start working. So I have, as I said, IDSS is equal to 8 milliamperes, and I have my VP is equal to minus 4 volts. So the first step, we said we just substitute for VGS equal to 0. In the equation, VGS equal to 0, so 0 over VP is equal to 0, and therefore I know that ID is equal to IDDS. We said it's equal to what? In that case, it's equal to 8 milliamperes. The next, we will go and substitute for VGS equal to VP. We said it's equal in that equation, VPB over VPB, that will be equal that ID is equal to what? To 0. So I am able here by those two, to get those 2 points. I was able to say that this is ID. I got for the value 0 for the case of VPP here. So this is VP, okay, which is VGS here. And here I have for the value of VGS equal to 0, I have the 8 milliampere. Now I cannot draw here just a direct straight line. In the curve we know it should look like this. So we need now to get some different numbers, and we can get that by varying the value. Let's say we take a value of -1 volt. So we'll just go to this equation. We say, okay, we have 1 minus 1 over 1 over 4. This is -4. So we just substitute. We have it from our curve, if you remember from the beginning. From here we said here it is Vp is equal to -4 from this one. So we will just say, okay, we will be able to calculate what is the value here. Therefore 1 minus 0.25 all squared will be this number multiplied by 8, and this is the value. Now if I want to change the value to any other value, I can do, of course, and I can continue, or if you wish you can try to see another relation which relates simply VGS to ID. It's the other way around, where I have ID here. You do some simple mathematical manipulation here. It's not difficult at all. What I can do, I can take square root of those sides, this and this one. So I will have square root of ID will be equal to, or let me just write it this way first. So I'll show you how we got this equation. It's very simple. All what I need to do is to just first divide both sides by IDS. So I will have ID over IDSS equals to 1 minus VGS over VP squared. Then I take the square root of this side and of this side. So what I will get square root of ID over IDSS is equal to 1 minus VGS over VP, correct? Then I do some mathematical manipulations, because what I care about only is to get VGS by itself. So what I will do, I will say, well, in that case I move this to this side, so I will be having VGS over VP will be equal, if I move this here, it will be equal to 1 minus square root of ID over IDSS, and then I cross multiply. I will get VGS is equal to VP multiplied by 1 minus square root of ID over IDSS. So it's easy. In that case, all what you need to do is just to try different values of ID and see what will be the corresponding value of VGS. So this is as an example. If I have this information given to us, IDSS equal to 12 milliampere, VP is equal to -6 ampere. Sketch the transfer curve for this case. So again, we said it's so easy, so simple. These are the information that we have. So the first thing we will do, we will say, we know that from the equation, as I just said, the equation says that ID is nothing but IDSS multiplied by 1 minus VGS over VP all squared. So the first thing we go and we substitute VGS equals to 0. That means ID will be IDSS. So for VGS is equal to 0, you have the current which is equal to 12 milliamperes. So this is the first point. Then we will just use VGS equals to VP, which is -6. So you will get a 0. So in that case, you will have here the second point. Now in between, it's up to you how you want to try it. Would you like to try for what will be the value of ID for, let's say, VGS equals to -2 as an example. So what I will get in that case, I will say I will have IDS or ID is equal to IDS, which is 12 milli times 1 minus VGS, we said equal how much? VGS is equal to -2 divided by -6 all square. So that will be 1 over 3, and therefore here I have 0.66 squared times 12 times 10 to minus 3 will be your ID. So you have a number, you substitute it here, and I can get it for the other ones. So you will be able to get a curve that will look like maybe something like that. These numbers are shown here. As you can see, we are just showing the cases. So this is the first case, this is the second case, the one, and as an example, if I would like to take minus 3 instead, so for minus 3 VGS you have, this will be 1/2, so 1 minus 1/2 all square, this is 0.25, so it's actually 1/4 times 12, it will be 3. So for minus 3 VGS you have a 3 milliampere, and you continue as I said, and you will be able to get your complete curve. Now if you just want to go and look at the cases where you have how are the specifications and how are the ratings, again as I said, this is one of the JFET transistors, it's 2N5457. You can see that you have 1, 2, 3, so 1 will be the drain, the gate will be number 3, and the one in the middle is the source. So that's important, and it's giving you here all values that you have. The drain source voltage, which is VDS, its maximum rating would be 25 volts. The drain gate voltage is 25 volts. The reverse gate source voltage will be, which is VGSP, is minus 25. The gate current is 10 milliampere. Be careful, it's only milliampere. And then you can see what is the total device dissipation at 25 degrees centigrade is around, in this range, it's between 310, you know, it's actually 310 milliwatt, but it will be derated if you change the temperature. Any value above 25, it will derate it for each degree centigrade 2.82 milliwatt. So this is something interesting that we just showed you, and here again this is how it's more a clear picture, where I said again the middle one here, as you can see, usually you take it and you look at it from the knob. As an example here shows that number 1 is the source, number 2 is the gate, and number 3 is the drain.